All right, final two chapters. I kind of bundled them together since I only suggested a couple problems from each chapter. Um, by now it's getting rather close to the end of the semester, so we're just kind of focusing on kind of some big picture ideas, kind of to kind of give you a little bit of an idea of kind of how we might extend some of the cool stuff we've talked about in this class. In case it tickles your fancy to go a little further. So regardless of your major, I would encourage you to give some consideration to potentially pursuing, we have a minor in applied statistics. So the minor actually pairs very nicely with a whole bunch of different majors. You got to take Math 121, which you've already done, so you're already like 1/6 of the way there. You got to take some version of calculus, and it could be any type of version of calculus. You got to take what's called, I think you got to take Stat 200, which is kind of like the natural extension of this Math 121. I know the numbers aren't quite sequential, but Stat 200, it's kind of like Stats 2. So if you really liked what we did here, I think you'll find STA 200 really useful. And then you take like 3 classes from like a really large pool of classes, and they're sort of intended to be kind of classes that are ideally from the major that you already have. So they're intended to be, how do we apply statistics in psychology? So there's actually a lot of classes that the psychology department offers, which is kind of like on statistical application, research methods, things like that. Um, so you gotta take basically 3 of these math classes, and then ideally three classes from your own major that are kind of focused on applying statistics in the context of your particular passion. So something for you to think about. Something else for you to think about is if you're getting close to graduation, and you're really digging the statistics, we offer a master's degree in statistics, an MS in applied statistics. Now, you may or may not have what's considered a quantitative major, but our master's program is very inclusive. So it is designed to be accessible to a very broad range of majors, not necessarily just math majors. So again, if you're getting a major in psychology, if you're getting a major in computer science, and you want to kind of learn how to apply these statistics in like your field of passion, I would encourage you to maybe kind of give me a shout out, and I could kind of tell you a little bit more about our master's program. In fact, if you're kind of like in that second, third year, the university actually allows some kind of flexible ranges and does allow you to kind of combine typically your 4th year of your bachelor's degree with like the 1st year of your master's degree. So instead of it taking 4 years to get a bachelor's degree and 2 years to get a master's, you can kind of overlap them and get both of them in 5 years. Um, so I mean that's kind of like a case by case basis. I can't promise you anything, but there is a lot of flexibility to make that happen. So I hope that you've enjoyed what we've done in this class. I find it a little bit challenging to completely communicate my particular passion about statistics in an online environment. I've done what I can, um, but it really is a pretty exciting profession. And I think the thing that's most cool about statistics is it really is like a nice sort of way of thinking. It's a nice set of tools for really supplementing any particular field of study or major. So no matter what you're interested in, I think statistics can play a big role and becoming more quantitatively minded, say getting a minor in applied statistics. I think in this kind of STEM, quantitative, kind of scientific, statistical, big data science day and age, it's a really, really nice way to kind of set yourself apart from your peers that you're going to be competing with to get, right, whatever the jobs are that you're out there trying to get. So anyways, enough about my sales pitch. Let's move on to the homework problems. I taught this a little out of sequence, felt more natural to me. So I actually taught chapter 13, and then I think I taught chapter 12. So we're going to start with chapter 13. Chapter 13, remember, is actually kind of revisiting a topic that we talked about before. I think all the way back in chapter 4. So chapter 4, we talked about correlation, but we also talked about this idea, this really powerful idea of something called simple linear regression. So simple linear regression is just a way of exploring a potential relationship between two numeric variables. And so we talked about a regression line. We talked about how the line has a slope. We talked about how the line has an intercept. But when we talked about chapter 4, we hadn't really developed the idea of hypothesis testing. So we could conjecture relationships between two variables, x and y, but we didn't really have a way of testing, of statistically testing whether or not there's a relationship between x and y. And so now that we've talked about hypothesis tests, chapter 13 brings us back to regression and says, hey, we can actually do hypothesis testing in the context of regression, and this allows us to actually answer a question, yes or no, is there in fact a relationship between two variables? So here's an example from our textbook, talks about ozone, apparently a major component of air pollution in many cities. A little bit of a technical kind of problem, unless you're kind of, I guess, a meteorological student or major. But they had this study where they looked at the mean percent relative humidity, whatever that is, I guess humidity, and ozone levels. So do ozone levels depend upon humidity? It's kind of the question they're asking. And so they took a bunch of samples, I guess maybe a sample every day. So every day they measured the humidity and the ozone levels. And then they ran it in a statistical computer. So, I mean, again, real statistics, we're not using calculators, we're using some type of software program. One somewhat common software program is something called Minitab. So the output, the results are given on the next slide, and their results as computed and presented by a software program called Minitab. And so there it is. So notice it gives us the regression equation at the very top. So, right, ozone is our y. So the amount of ozone we're saying is 88.761 minus 0.7524 times x. X is our humidity. A negative slope basically means that the more humidity, it means a negative relationship. So the more humidity, we expect less ozone, right? For every 1 unit increase in humidity, we expect ozone to decrease by 0.7524 units. And then we had that stuff before. It's actually just kind of reiterating it. So it says the constant's 88.761. That's just a y-intercept. It says the humidity, that's just the slope it's referring to, is negative 0.7524. So we saw that already. Now, really what's of interest to us is the p column. So the p column is the p-value, and we usually only care about the p-value for the slope. So it's that bottom right number. It says 0.000. It's actually not 0. P-values can never be 0. It's basically just saying it's sort of immeasurably small. Less than 0.001, essentially, is what it's telling us. So it's a very, very sort of immeasurably small p-value. So we'll see what that means on the next slide. So we already said this. Slope is negative 7 or negative 0.7524. There we go. The y-intercept is 88.761. The p-value is listed as 0.000, but again, it just means it's really small. But regardless, anything less than 0.000 is going to be less than 0.05. And since it's less than 0.05, we reject the null hypothesis. That's the same. It's how we've always been doing hypothesis tests. What does it mean to reject the null hypothesis in the context of regression? It basically means that there is evidence of a relationship. When we reject the null hypothesis, it basically means we think the slope is something other than 0. And so if the slope is something other than 0, that's basically saying there's a relationship, a linear relationship between these. Or put another way, there's sufficient evidence to conclude that relative humidity, that's our X variable, is useful in predicting ozone levels. That's our Y variable. Here's an extension, same context, just going a little different. It's nice to take a look at, but to be honest, probably the type of problem you would see on a test is probably the first type of problem we just solved. That said, I think it's still worth, right, solving this problem, number 19. It's still talking about ozone and humidity, but it's focusing on doing prediction. So here we want to try to predict the ozone level when the humidity is 60%. It talks about doing 95% prediction intervals and 95% confidence intervals. So, right, again, that's something that we could ask a software program to do for us. And in this particular example, the textbook has some output, some results from the software program Minitab. So on the bottom, it says humidity 60. So that's basically just saying that all of these values that we're seeing, all these numbers, are calculated under the assumption that X is equal to 60. Where it says the fit is 43.62, that's basically just saying that that if our X, if our humidity is 60, then we predict our Y, that's the ozone amount, to be 43.62. And then we have two intervals over there. We have a confidence interval, the CI. We have a prediction interval, that's a PI. They're subtly different. So the confidence interval is the idea, like for all days that have a humidity of 60%, what is the average ozone amount? And here we're basically saying that we're 95% confident that that average ozone amount is somewhere between 41.23 and 46. The prediction interval is basically, right, instead of like an average, it's like a single day. So if we have just a single day, any one day where the humidity is 60, what do we predict the ozone is for that one day? And here we're basically saying we're 95% confident that the ozone amount for any given day with a humidity of 60 is somewhere between 20.86 and 66.37. Probably I summarized that on the next slide. Let's go take a look. Yeah, so I think this is everything I just said. I'll let you kind of read through. Our point estimate, our best guess, that's the thing that was called fit for the mean ozone level for days when the relative humidity is 60% is at 43.62. The interval is 41.23 to 46. Also, we would predict the ozone level to be 40. Oh, shoot. The number in A and C should be the same, and it should be that fit value. Yeah, I don't have the book in front of me, sadly. So it should either be 43.62 or 42.62, whichever one it said. I'm actually trying desperately to thumb through this textbook as we do this problem, so I can make sure I can verify the number correctly. Yeah, whatever it says. I mean, you can look it up. So those numbers should be the same. I apologize for the typo. And then our 95% prediction interval is that 20.86 to 66.35, 37. Notice 80 is not inside that interval. And so we don't think that that's a reasonable prediction, right? If someone predicted that that the ozone would be 80 for a day in which the humidity was 60, we would say, no, I don't think that's realistic. I don't know what it's going to be, but I'm 95% confident it's going to be somewhere between, say, 21 and 66. And since 80 is not in that interval, right, we don't think 80 is a particularly plausible number. Easy enough? Ha! I did look it up. So it should be 43.62. So A is correct, C is wrong. I apologize for that. And that's chapter 13. So that's kind of just going a little bit deeper. Kind of, again, I guess the kind of idea is like we're looking at different types of hypothesis tests. So, right, that's kind of how we can use hypothesis testing to enrich our exploration of regression. That is our exploration of relationships between two numeric variables. Chapter 12, kind of the idea is exploring relationships between two non-numeric variables. So here, kind of the same idea. We're looking at relationships between variables, but instead of quantitative variables, instead of numeric variables, we're looking at qualitative variables or categorical variables. And again, the class is winding down. There's only so much time. We've already had to absorb so much material. So I really kind of just focus on a very big picture overview of this stuff. All right, so first problem. A researcher wants to determine whether children are more likely to be born on certain days of the week. So she samples 350 births and records the day of the week for each of them. The null hypothesis is that a birth is equally likely to occur on any day of the week. And so it asks us to compute something called expected frequencies. So basically the idea of expected frequencies is okay. Under this null hypothesis, under this conjecture that births are equally likely any given day of the week, how many births do we expect on any given day? So that's pretty straightforward. We have a total of 350 births, 7 days in a week. If all days are equally likely, then sort of the probability of falling in any day would be 1 in 7. So, right, under our null hypothesis, we would expect 1/7 of the 350 births to occur on Sunday. If we plug that into our calculator, we should get the number 50. So we expect 50 on Sunday. And 1/7 of the 350 on Monday, and 1/7 of the 350 on Tuesday, and so on. So again, it's really just kind of like if we expect them to be equally likely, then we expect the same number on every day of the week. So the only way that we can have the same number and have them total up to 350 is if every day of the week there's 50 births. So that's what we would expect to see. Now, of course, that may or may not be what we actually see when we take our sample. And so what we're really doing is we're taking our sample and we're seeing sort of how close our sample is to kind of what we expect it to be. Are all the days 50 or very close to 50? Or are some of them very far from 50? If some of them are very far from 50, that would maybe refute our null hypothesis, our conjecture that you're just as likely to be born on a Sunday as you are any other day of the week. All right, next problem is number 7. Number 7 is one of those like generic problems. Again, I always try to like come up with like my own context. It helps me to have like some type of application. Makes it less theoretical. So I don't know, imagine maybe we have a 5-sided die. So it says that we have these outcomes, 1, 2, 3, 4, 5. Let's imagine that it's just a die, like a weird kind of die. We roll it and we get a number 1 or 2 or 3 or 4 or 5. And right, again, so it's weird in a few ways. It's weird in the fact that it has 5 sides. I'm not even sure that that's like geometrically possible. But whatever, in the theater of our imagination, anything's possible. Also, it's not like a fair die. So we have this sort of expectation. That's kind of what's communicated to us in part A, that we have a 30% chance of rolling a 1, and a 25% chance of rolling a 2, and a 20% chance of rolling a 3, 15% chance of rolling a 4, 10% chance of rolling a 5. So, right, it's kind of the die is kind of weighted in a way that it's more likely to get low numbers than it is high numbers. And so A asks us to do expected frequencies, which is kind of what we just did. It's just now our probabilities are different for each outcome instead of just being 1/7 for every outcome. So notice that the size of our sample is a total of 70. So right, if you look at the very top of the problem, it's basically saying that we rolled this die a whole bunch. We got 25 ones and 14 twos and 23 threes, 6 fours, 2 fives. If we add all those numbers up, we get 70. So we've rolled the die a total of 70 times. So basically what we're saying is expected frequencies are okay. If it really is, if you really have a 30% chance to roll a 1, and if you rolled this die 70 times, then you would expect 30% of those 70 rolls, which turns out to be 21, to be the number 1. Does that make sense? And 25% of the 70 rolls, which is 17.5, we don't round it, we leave it there, to be the number 2. And 20% of the 70, which is 14, to be the number 3. We expect 10.5 number 4s, and we expect 7 5s. So there's A. And then like all the follow-up things basically just say like, okay, so now like test the person's claim. So the person's claim is that there's a 30% chance of rolling a 1 and a 25% chance of rolling a 2 and so on. Do we think this claim is true, yes or no? And so to do that calculation, we need to use your calculator. We need to use something called the chi-square. So it's not really an x, it's really this kind of Greek symbol chi-square goodness of fit test, which is under our stat test menu. Now, before we actually do that test, we got to put some information in the calculator. And we put that in something called lists. It's not something we've used in this class, may or may not be something you've done in another class. Either way, I'll walk you through how to set up the lists. So to set up your lists, the first thing we do is we hit stats. But instead of going over to tests, we stay in that edit section. And we're going to actually pick option 1, which is edit. It's going to let us edit our lists, which in our case is just put numbers into our lists. Incidentally, sometimes students, after they've done this once or twice and they've like filled their lists up with numbers, and they have a hard time clearing it out. They have a hard time putting new numbers into their lists. Notice option 4 is clear your list. So, right, once we finish this problem and we wanted to start a new problem, we would pick option 4 to clear our lists. So I pick edit and I have these lists, these L1 and L2. So L1 is the actual frequency. So it's the number of observations that fell into each category. So if I look back at the top of the problem, I had 25 observations in category 1. I had 14 observations in category 2, 23 in category 3, 6 in category 4, and 2 in category 5. The second list is going to be under our null hypothesis, under our conjectured probabilities, what would we expect to be in each of those categories? And we calculated that already. That's what we calculated in part A. So again, I'm just taking these from the previous slide. We had 21, 17.5, 14, 10.5, and 7. Okay, so that fills our lists in. Now we hit the stat button again. So we have our lists filled in. We're actually ready to do the test now. So hit stats again. Go over to tests, because this is useful on a test, and go to that chi-square goodness of fit test section. So option D. And there's not a lot to fill in, right? So basically you say, okay, which list has your actual observations, your observed observations? That was list 1. which has your expected observations. That was list 2. And that should be set up by default. You shouldn't actually even need to put those in there. That should be just what your calculator kind of says naturally. Then there's degrees of freedom. Again, degrees of freedom are a little technical, but what we want to put for degrees of freedom is always one less than the number of categories. Oh, dear me. Yeah, bad professor. I apologize. It's tough to change it once I've actually embedded this as a YouTube video, so it may just have to go out into the internet being wrong, and I apologize for that. So we had 5 categories. Your degrees of freedom should be 4. It's always one less than your number of categories. I don't know why. When I read this problem, I was thinking 6 categories. And that's why I put 5. But in fact, there's 5 categories. So again, degrees of freedom should be 4. I'm so sorry about that. So there's the results of our goodness of fit test. They're not quite right. I mean, changing the degrees of freedom to 4, I encourage you to do it, shouldn't change our numbers a whole lot, but it will change them a little bit. The top thing where it says chi-square, the 12.74, that's our test statistic. But more importantly, more useful is that p-value. So that p-value is 0.02586. So there it is. Our test statistic is 12.75. And see, there's where I said since we have 6 categories, but really we had 5 categories. So our degrees of freedom should have been 4. Yeah, statistics, a lot of fun, but not easy. You could be a PhD professor and still get it wrong. Let's use the p-value that we had. Our p-value that we had was 0.0259. That's less than 0.05. So we at that 0.05 level, we would reject the null hypothesis. Rejecting the null hypothesis means that there is sufficient evidence to conclude the probabilities are different than conjectured. That claim about being a 30% chance for a 1 and a 25% chance for a 2, we don't believe that claim. However, then the book asks us to do the hypothesis test with a more rigorous, more stringent alpha level. Instead of the usual 0.05, it asks us to use 0.01. If we use 0.01, well, hey, now our p-value's more than alpha. So in that case, we're going to fail to reject it. In this case, we would say there's not sufficient evidence to conclude the probabilities are different than conjectured. Right, that 0.01 is requiring more evidence, and we don't have that much evidence to conclude the probabilities are different than conjectured. And there we go. That's the last problem from the last chapter. Ending on a low note, me getting a problem wrong, but I guess at the very least kind of catching it along the way. So hopefully you don't make the same mistake when you end up taking your exam, probably in just a little bit.